Well, last time we were actually, we took a moment last time to kind of have a bit of a chat about next semester's content. Did anyone have any follow-up questions from that? Think of anything over the weekend or anything? All right. The very last thing we talked about was this program here, which was a linear search. And the big thing I was trying to show you was, here's a linear search in Python, and here it is in Java. And your knee-jerk reaction is, yeah, it's different. But if you take 2 more seconds to look at the code, you realize it's not. It's just syntactically a little differently, but semantically it's the same. It's just a function definition. You've got the loop, you've got your if statement, and then your returns. Function definition, loop, if, returns. We looked at C# as well, which was actually identical to Java. Definition, loop, if, returns. C++, definition, if, loop, if, returns. Definition, loop, if, return. The big difference here with C is the arrays don't really know how big they are, so we keep track of that in a separate variable. But then we saw this one, which was, of course, okay, this is a little different. And yeah, this one was different. I mean, the underlying idea of the algorithm is the same, but the implementation is admittedly quite different than what we're used to. And it actually included an interesting new idea, but it's not new. The idea that this used, and remember, I wrote this in Python, but the idea that this used really wasn't new. Nothing about the code I wrote was showing you something like elementary new thing. No, if you've never seen it before, you should have been able to follow the code. But of course, there was some weirdness to it. But the weirdness really wasn't a new idea, but it definitely felt new. And let's start today with a quick activity. I want you to write a function. This should be easy. I'm going to give you like 3 minutes to do this, and that should be plenty of time. Maybe 4 minutes. I'll be nice. I'm going to give you 4 minutes. And I want you to write a function in Python that takes some integer n. And I want you to have that function return the sum of all numbers between 0 and n inclusively. Meaning, if you say 5, I want it to include 5 in the sum. I want it to be 0 plus 1 plus 2 plus 3 plus 4, n plus 5. If I gave it 10, I want it 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. So just write a function, takes an n, and returns the sum of all those numbers between 0 and n. Just write that function. I'll give you a few minutes to do it. This isn't a trick question either. I want to be very clear. Just write this function.
What format do we return it as?
Just an integer. Just return the sum. Raise your hand if you're done. Raise your hand if you're done in like 30 seconds. Okay, 30 more seconds. Whose looks more or less like this? Yeah, that's what I thought, right? Now I could have done it with a while loop. I had to do n plus 1 here in order to have it include n, because of course range would go all the way up to but exclude n. If you wrote this algorithm and you didn't include n, you made it exclude n, whatever, not that big of a deal. Just the point is, there you go, right? Did anyone do it with a while loop instead? Yeah, whatever. Same difference. They're equivalent effectively. Now, you know what's interesting about this one is this problem. There's an interesting property about solving this problem. And it's that, you know, if I'm looking for the sum up to 5, but I already know the sum up to 4, so I already know the sum up to 4. How do I get the sum up to 5? Yeah. If I have the sum all the way up to 4, all I have to do is add 5 to that, and it's the sum up to 5. In fact, if then I wanted the sum up to 6, what would I do? The same thing, just add the 6 up to the sum up to 5. If I wanted to know the sum up to n, all I need is the sum up to n minus 1, and then I add n to it, right? Look, the looks on your faces, I can't tell if you get what I'm saying or not. I see one thumbs up. So the sum up to 4, right, is 0 plus 1 plus 2, which is 3, plus 3, which is 6, plus 4, which is 10, right? So the sum up to 4 is 10. And so if I know the sum of 0 to 4 is 10, and I want to know the sum up to 5, I just take the sum up to 4, which was 10, and add 5 to it, which is 15. Therefore, the sum up to 5 is 15. Right? Raise your hand if you're like, yeah, obviously. Okay, I can't, so, All right. And you know what else is interesting? Maybe this one's not interesting. Maybe this one's just kind of like an obvious matter of fact. If I said 0, what's the sum? It's 0. Yeah, so the sum, if you told me the sum up to 0 is, well, I just know it's 0. That's just the way it is. But if I told you what's the sum up to 1, well, it's the sum up to 0. In fact, that's actually, if I want to know the sum up to 1, let's substitute that n thing, right? If n is 1, what is n minus 1? But I know the sum up to 0. What is the sum up to 0? Did you just say 2? 0. Okay, good. Did you say 2? Oh, for some reason I heard it too, and I was like, I don't know how that gets into this. So you know what's interesting? Let's say I want to know this. Let's play that game with n, except let's substitute n for 2. What's the sum up to 2? Well, I know it's the sum up to 1 plus 2. But what's the sum up to 1? It's the sum of up to 0 plus 1. So I could write this a little differently. Checks out. Looks good. That code makes perfect sense, right? There's nothing in here that's new. Look at this code and make it make sense. Do you have any questions about this code, or does it make perfect sense? When n is 0, it's just 0. Otherwise, if I want to know the sum up to 5, I just need to know the sum up to 4. And the good news is I've got a function that'll calculate the sum up to 4 for me. I just have to call the function sum2, but give it the 4. Yeah.
Why are you doing n minus 1 when you have to do n plus 1 for the other ones? Shouldn't it just be n?
Well, I want it to be n plus the sum up to n minus 1. So imagine I put in 5, right?
It would only sum up to 4 then.
Well, it would be 5, n is 5. So this function returns 5 plus sum to 4. Sum to 4 will return the sum up to 4. I add 5 to it. It gives me back 15. It's the whole thing.
So it's kind of like go up levels like Inception.
Well, it actually kind of goes down and then back up.
Yeah, it'll go down to the bottom, and then once it gets, like, eventually it'll reach like n is 0, so it'll return 0, and then it'll add 1 to 0, and keep going.
Yeah, let's try to draw this. I'm going to try to whip out my paint skills. So I'm just going to represent this function as f, just because I'm lazy and I don't want to write it. I want to know f of 5, right? And well, f of 5, well, that's just equal to 5 plus f of 4. Easy peasy. But then you say to me, well, hold on. I feel like you're skipping some steps here. You're saying it's just 5 plus f of 4. Where the hell's f of 4? Oh, no problem. We got a function that calculates it. It's f. Just call f of 4. So here, f of 4 equals 4 plus f of 3. Great. And then again, you're saying, what the hell is f of 3? No worries. We got a function to calculate that. We just call the sum2 function. Whoop. Three plus f of 2. But what's f of 2? Well, no worries. That's easy. It's just 2 plus f of 1. Easy peasy. And what's f of 1? Well, I got to make my screen a little bigger here. Whoop. F of 1 is just 1 plus f of 0. And remember, if you're like, but how did I know it's 5 plus f of 4? Well, that's how the function was written. It's n plus f of n minus 1. Right? So in order to know f of 1, I just need to add 1 to whatever f of 0 is. And what's f of 0? Well, that's that special case. When n is 0, it's just 0. I don't need to calculate anything at all. But now I know what f of 0 is. It's just 0. Meaning f of 1 is just 1 plus 0, which is 1, which is great. Now I know f of 1, if I can see my mouse, is just 1, which is great because now I know f of 2 is just 2 plus 1. Now f of 3, well, that's easy. It's 6 because it's 3 plus 3. I can't see my cursor. And f of 4, well, that's great because I now know f of 3 is 6, so it's just 4 plus 6, which is 10. And then f of 5, well, that's 5 plus what f of 4 was, which was 10, and it's 15. It's easy, right? Who here thinks this is a little weird? Come on, be honest. You don't think it's weird? I think it's kind of weird. It is weird. So I want some questions now. Well, I'm sure you have some questions. What do you think of this? Comments, thoughts, concerns, observations, notes? What you got? Say that again. I'd argue this is a simplification of what we've been doing. In fact, I would very strongly argue it's a simplification. The only difference is you're used to doing it the other way. You're not used to doing it this way. If you were used to doing it this way, the other way would be weird. In a programming language like Haskell, you're not allowed to use loops. Loops don't exist. You have to do this type of thing. I spent a year only using languages like Haskell, and when I had to go back, I went back to C#, which has loops. It was hard for me to go back to loops. I couldn't wrap my head around loops. It was weird. Any other thoughts on this? Questions? Whatever? The magic of this is we've got what we call a base case, which is just kind of like this matter-of-fact case. 0. When you want to know the sum to 0, I know it's 0. Great. Otherwise, for any general one, Sum 2 is just n plus the sum up to everything excluding n. That's the general n. Does this look familiar to anything you've seen before? Any proof strategy you're used to? Does this look familiar? Who said induction? Yeah, this looks a hell of a lot like induction, doesn't it? Yeah. Raise your hand if you know what induction is. Yeah, I'm not going to get you. Raise your hand if you've heard of induction before. Okay, I'm surprised. You do in discrete math? I thought I did it in high school, to be honest, but I thought I did in high school. I thought that was like high school level stuff, to be honest. Pardon? You did not do that in high school? Well, not this, but not induction. Okay. Well, whatever. We call this type of thing recursion. And the reason it's like recursion is like we are defining something in terms of itself. The function definition of sum 2 includes a call to the function that I'm defining. The function sum 2 calls sum 2 within it, which is weird, right? Let's do another quick little exploration here. What's going to happen when I hit run? Don't yell it out. Take a moment, look at this code. What's going to happen? And if you're like, how am I supposed to know? You have every tool available to you to understand what's going to happen. You should be able to figure out, like, you absolutely should understand what this will do. Raise your hand if you think you know what it's going to do. Really high, I want to see. Let's talk through this. I call it with 0 on line 5. I go up. What do? I go into the function, n is 0. What happens? We print out 0. And then we just call the function uh-oh with n plus 1. Well, what's 0 plus 1? All right, so we go into uh-oh, and now n is 1. What gets printed out? And then we call uh-oh again with what's n plus 1 here? We print out 2. And so on, and so on, and so on, and so on. What's this going to do? Nope, it actually crashes. We counted to 953. Now this right here, we got an exception actually. And this is a special type of exception. It's called a recursion error, maximum recursion depth exceeded. We're calling a Python object. And this is actually an exception enforced by the programming language. There's nothing in the natural property of our universe where it should say this should break. This is just how Python's designed. Now this exception goes by a different name in many other programming languages. Does anyone know what this exception is called in other programming languages? It's very famous. You've all heard it before. I know you have. Well, it's one of those, but we can get more specific. It's called a stack overflow. It's called a stack overflow exception. That's what this is. So if you're wondering, oh, stack overflow, oh, that's where it got its name from. Here, let's just let's just write a function to count using recursion, just for fun. It's going to be rather silly, because if I just say, you'll see. One. No, this isn't a great example. Let's do a little exercise here. I want to know 1, 2, 3, 4, 5. Perfect. The 5 of you I'm using as guinea pigs here. So you got to participate right now whether you like it or not. Don't worry, it's going to be easy. Here's what I want to know. All right? I want to know how many people are sitting over here. Obviously, I can see it's 1, 2, 3, 4, 5 people. Okay? And by the way, the pattern we're going to go is up this way and then my left to your right. You'll see. So I want to know how many people are in this row, or in this block of seats right here. So I'm going to ask you, how many people are there? And you're going to look behind and you're going to go like, oh shit, I don't know. But you do know that it's you, which is how many people? 1, plus how many people are behind you, right? Would you agree with that statement? However many are there, plus you is the total number of people in that row. So you got to find that out, how many people are behind you. But you know what? You don't want to find it out. So what you're going to do is you're going to delegate that work to him. You're going to ask him, hey, how many people are there in that row behind you? So go ask him.
How many people are in the row behind you?
So what you're going to do is like, oh, great, I don't want to figure this out. You're going to say, well, it's you, which is how many people? 1, plus however many other people are there. So how are you going to find that out? Well, you're not going to. You're going to ask him to do it. So ask him. So you're like, shit, I don't know. But you do know it's you, which is how many people, plus the number of people behind you, which is, well, you don't know. So you're going to ask her, how many people are there behind you? And you go, I don't know. I don't want to figure it out. But all I want to do is say, well, it's you, which is how many people? Plus how many people behind you. And well, so you don't want to figure that out. So you ask the guy behind you. Ask him. So you go, well, it's you, how many people? Plus how many people behind you? Ah, yeah, there's nobody behind you. So you're like, well, that's easy. It's just 1. So now you can tell her, oh, it's just 1. And you go, oh, great, so it was 1 plus you, which is how many? Great, so now tell him. And you go, perfect, it was 2 plus you, which is how many? Great, now you tell him. So 3 people plus you is how many people? So there's 4 people total, you tell him. Then you go, great, well, it's 4 plus you, how many? 5 people. There's 5 people over there. Not a single one person counted everybody. They just counted themselves and asked everyone behind them how many people were there. It's kind of weird. We just counted with no one really counting. I mean, they added 1 to the previous number. I mean, like in total, you put it together, all that work in total counted everybody. But you know, each step along the way, everyone just delegated the rest of the work to the next guy. Which was way off. That's awesome, right? This recursion, this way of iterating, first of all, anything you do with a loop, you can do with recursion. Anything you do with recursion, you can do with a loop. Someone last time asked, is this a faster way of looping? And this is tricky to answer. Because when it comes to computation as a mathematical construct, right? All of these definitions of all of the computing we ever do is all formally defined like mathematically. And when it comes to recursion versus like iterating with a loop, one is not intrinsically faster than the other. It's irrelevant. It's just a process. But in practice, on the computing machines we use, by the nature of how they are built and engineered, recursion is slower. It is, technically. Within the rules of our universe, it's not. That's not a thing that's just fundamentally true. Recursion is not fundamentally a slower process. It's just by design of the computer, it's slower. But you want to hear something wild? Most processes in nature that are iterative are recurrent. Anything in nature that's like iterative, any pattern you see, that arises like iteratively, it's recurrent. It's not, there's no for loop anywhere. Ice crystals don't form based on a for loop. No, they're forming based on the crystals that are already there and following some simple properties, and then you get this interesting pattern arising. Recursion is far more natural in our world than a for loop is. It's kind of wild. If I spent this first semester teaching you to program in a programming language called Lisp, which some universities will use that. Anyone know what Lisp stands for? No, never mind, it's a dumb joke. But that is a programming language that's like Haskell. And your brain would be now like wired to loop with recursion like this. Now, there are some things, based on the time, and really this is not on the exam, don't worry. Like, you don't need to freak out. I just went on a bit of a tangent right now to show you an interesting thing. We're going to spend a lot more time with these ideas next semester. But recursion, I think, is pretty neat. Anything you do with a loop, you can do with recursion. Anything you do with recursion, you can do with a loop. Sometimes the algorithm, like recursive algorithms tend to be like elegant too. Like there's a niceness to it. Programmers just tend to like recursion. There's like a beauty to those algorithms a lot of the times. And I was saying anything you do with recursion, you can do with loops and vice versa. But just because you can doesn't mean you should. And rest assured, actually, for in many programming languages, Java included, your compilers, the program that takes your code and turns it into the stuff that actually runs on your computer, will actually do like tail-end recursion optimization. And what it'll do is it'll actually convert your code. The instructions that's actually running is going to be actually a loop, even though your code was recursion. Because the loop will be faster, but sometimes the code is much nicer when it's recursively written. So just neat observations. Anyways, any questions about recursion there? No? All right. All right, warning. We're going to talk about sorting algorithms. Have you ever sorted anything before? Put your hands up. Of course you have. Everyone's sorted something before. And whether you like it or not, you followed some sort of algorithm. But have you ever really thought, what were the steps I did one at a time to sort this thing? Now, just as a warning, we're going to look at some algorithms here in this topic. We're probably not going to get to much today. But we're going to get to some algorithms here in this topic, and they're not overly complex. They're not simple. They're not easy to understand, that's for sure. But no one's expecting you to look at the code and know what it's doing like that. No. This code that you're going to see, these algorithms, they're going to be sophisticated enough. They are absolutely non-trivial algorithms. you're all equipped with the requisite skills to understand everything there. They do require careful study to understand really what's going on, and the best strategy for approaching these algorithms is carefully trace through their operations step by step, making no assumptions, as you should always do when looking at this stuff. But just a reminder, these are non-trivial algorithms. Yet at the same time, you clearly all know how to sort things. So you've clearly demonstrated your ability to understand this, whether you like it or not. So now, take a moment, think to yourself, what were the steps that I followed to sort those things? Imagine I gave you a pile of exams, and I wanted you to sort them alphabetically. How do you do that? I'm going to give you a few minutes, think about it. Feel free, talk amongst yourselves, maybe talk to the person next to you, explain how you do it. But take a few minutes and think about it. Try to describe the algorithm that you followed to sort things, because you've all done it. Hell, my 3-year-old can do it. You can. What steps did you actually follow, though? So think about it. Now, to be clear, how many ways are there to sort things? Like, how many algorithms are there to sort a collection of things? A lot, yeah. Some are going to be better than others. Some are going to be better than others sometimes and worse than others other times. Some are going to be effectively the same as others. And some are going to be just terrible. But let's take a moment and talk about it. So raise your hand if you explained if you have a sorting algorithm in your head right now, really high. Okay? Great. So you, describe it to me. Okay, start again. Say that again. Let's pretend it's a list of numbers for ease, okay? So it's a list of numbers, they're not sorted. I want to sort them. Does that ruin it? All right. Okay, what do I do? So do like a scan and look for the lowest number. And bring it to the top. All right. Now what? Do that again. And again and again and again. Okay, cool. Yeah, that's called selection sort, actually. That's an existing sorting algorithm called selection sort. Very good. Everyone give them that's a good one. Yeah, very good. Well done. I'm not gonna lie, usually people, they give me bullshit garbage that definitely won't work. That'll work. Good job. So now the pressure's on. Raise your hand if you have one in your head again. Yeah, now less people put their hands up because they know what I'm doing. All right, what do you do? So, okay, say that again.
The question was, right, that like you got a bunch of papers and you got a list in alphabetical.
Sure. I mean, for simplicity, for his example, I said it could be a list of numbers if that helps you. But if you want it to be the exams, it can still be the exams. Okay, start again saying it with letters. So we're sorting exams with names on it.
Yeah, so I would take the ones, I'd take a pile and put A, and then B, and then C.
So you put all of the,
Letters together.
so you take all of the exams that have an A, and that start with an A, and you put it in a pile. And you do the same thing with B. Okay, great. Now what?
And then once I do that for all the letters, I just take A, and then put it on top of B, and then put it on top of C, and then get it done.
Okay, so that's called like a bucket sort. But there's a problem with that sort. Your list is like your pile of exams isn't sorted. It's kind of sorted, but it's not fully sorted because of what about all those A's? You never sorted that bucket of A's.
Well, no, I was going to say, I can take the A, because I find if I had a big pile, and then I tried to, okay, so I'm going to sort it. I'm going to take one that says G on it, right? And I already got my pile with like the full one alphabetical, if I'm going to do it like that. I need to search through every single one just to find where the G's would be and put it in there.
So,
Instead of doing that, I just have my own pile. It's a lot easier to sort.
okay, so you've got the buckets though, but I've got a bucket of A's, a bucket of B's, a bucket of C's. And if I were to take each of these buckets and stack them on top of each other, I would be like sorted alphabetically, kind of. Oh, you could do the same thing with the second letter.
Until you know that they're all sorted.
Okay, interesting. Okay, there you go. So you could just keep going until you know they're all sorted. So if it's like AA, well, you put into the A bucket, a B bucket, a C. I see what you're saying. Okay, yeah, that'll work. Yeah. In fact, that sort you did, that bucket sort, the first step is brilliant. It's a really good sorting algorithm. And it's really efficient, but there's a trade-off in that, like it won't be fully sorted. Like if I stopped after doing the first one, it won't be fully sorted, but sometimes that's good enough. Like if I have 100 exams, and we're going to learn this, the number of steps it takes to sort using these sorting algorithms is quadratic. But that's linear. But it's not perfect, but it's good enough. And the reason I like to do it like that is because when someone comes to office hours and they say, can I see my exam? I've got a stack of exams. They're not perfectly sorted, but I know all the A's are together and all the B's are together and all the C's are together. So at least I can search for your name pretty easily. So it's a great sorting algorithm. But you also described another sorting algorithm a little bit. Imagine I had an already sorted stack of exams. And I said, uh-oh, you forgot one. Add it. How do you then, what do you do? Say it again? Yeah, so like you kind of do like a linear search, let's say, to find out where does this belong? Yeah, so that's actually called an insertion sort. So he said selection sort, and you kind of mentioned a bucket sort and an insertion sort. So very well done. Everyone, he deserves like a really good round of applause. Very good. All right. How much time we got left? Anyone else have did anyone think of a way to sort things in a little differently? What do you say? Okay, but I'm not asking what sorting algorithms you know. I'm asking how would you sort these things? The bucket sort, yeah, okay. Did anyone think of another way to sort things? A little easy way, yeah?
So I take the first test exam, hold it up, and then the next one, if it's before after, then put it before after, and then the next one I go before after, and then if there's another one before after, you just keep doing that for all of them.
So you basically look at adjacent pairs, and if they're out of order, you flip them. Is that what you're saying? Okay. So I'll do that, but you know, if I do that, let's see if we can do this really quick here. Can I help you? Well, this class is about to end, but you're what did they say? All right. Too bad they didn't walk a little closer and their face wasn't like right in the camera. All right. Well, they spoiled the fun. We can't get to bubble sort right now. Rats. We'll pick up here on Friday, because tomorrow we have a special lecture tomorrow. Really interesting stuff. You'll love it.